Hello everyone, welcome to aplusbi. This channel is all about complex numbers, and in this video we're going to be solving a nice logarithmic equation with complex numbers. Logs are fun, complex numbers are fun, and logarithmic equations with complex numbers are more funner. So we have ln iz equals I times the quantity pi over 2 minus 1. So we're going to be solving for z values, and there's probably a couple different ways to approach it as far as I know. Let's go ahead and find out. All right, for the first method, I'd like to do the following. Since we have the ln of something, I want to use an identity. How about e to the power ln w equals w? Nice. So we can kind of do e to the power both sides. And the fact that we can do e to the power both sides comes from the well-definedness of functions. I don't know if that's the right term, but if you have something like z equals w, and if you apply a function f of z should also equals f of w. It's not always the other way around, because that would imply injectivity or one-to-oneness, but this forward direction is always available or valid or whatever you want to call that. Okay? So we're going to go ahead and use the definition. E to the power ln iz equals e to the power I multiplied by the quantity pi over 2 minus 1. Nice. What do you get from e to the power ln iz? Do you z what I z? Okay, that didn't work, but let's just pretend. What about the other one? E to the I times. Now, you got to remember Euler's formula, which is super important here. And if you're new to complex numbers, go ahead and check out my lecture videos. If you like algebra and number theory problems, especially at the complex, did I say complex? Sorry, I got stuck with complex. The competition level. Then go ahead and check out my other channel, Cyber Math, Cyber with an S. All right, cool. Now, what is Euler's formula? It is e to the I theta equals cosine theta plus I sine theta. So whenever theta is, whenever I is multiplied by something and it's in the exponent, that theta is basically the argument of the complex number, which you can plot in the argon plane. So let's suppose we have a complex number like this, because they're two-dimensional complex numbers. So they don't always appear on a number line. They're just kind of like vectors. And this is the real part of the argon plane. This is the imaginary part. And this is called the theta. And this is z, and r is the modulus or the absolute value. So theta is the argument, the angle. Okay? So what is I being multiplied by? Pi over 2 minus 1. So is that our angle then, the argument? Yes, but pi over 2 minus 1 is not a special angle, is it? So let's do this instead. How about writing this as e to the power I pi over 2 minus I, in other words, distribute the I, right? And then, since the exponents are being subtracted, I can kind of turn it into division or multiplication with a negative exponent, like e to the power I pi over 2 times e to the power negative I. Awesome. Now here's the fun part. What is e to the power I pi over 2? Think about it. We just talked about it, right? If the theta is pi over 2, then you are on the imaginary axis right here. And that just means that, there's no number in front of e to the I pi over 2, the modulus is 1. So you're 1 unit away from 0, but in the vertical direction, that is just I. Make sense? So this is I, and I has infinitely many representations because of the multiplicity or multi-valued nature, but this expression right here has a single value, and it's I. Make sense? And by the way, I is the imaginary unit, which could be defined as I squared equals negative 1. Some people call it the square root of negative 1. Yes and no. It's kind of like a gray area. I would say, even though the principal square root is defined as negative 1, it's kind of, I don't know. Anyways, let's not get into that. It's kind of like a gray area in my opinion. But this is I, okay? No doubt about it. So that's really good. You know why? Because from here, you get z right away. Look at that. I cancels out because, why does I cancel out? That's a good answer. Because it's not 0. Exactly, right? So z equals e to the power negative I. So that's the answer? Yes, but let's use Euler's formula, shall we? What does Euler's formula say? E to the I theta is equal to this. So what is theta here? You might be thinking, what is theta? Well, theta is -1. You like that? It's -1 radians. Don't forget, it can't be in degrees, it has to be in radians. So this is my theta. How am I going to write it in standard form? Well, cosine of -1 plus I sine -1. Because the formula again says e to the I theta equals cosine theta plus I sine theta. Make sense? So that's z. Great, but what is sine of -1? Sine is odd. Weird, right? But cosine is even, so cosine is going to absorb the negative. So we can write it as cosine of 1. I don't have to use parentheses, but I feel like it's better. And again, 1 radians, not degrees, okay? Be careful about that. So this is going to spit out a minus sign and will be sine of 1. That's why we don't use the degree symbol. Be very careful because they are different. By the way, I just remembered there was a really good question in an Olympiad book asked to compare sine of 3 radians and sine of 3 degrees. Easy question, but it's a good one because you kind of have to work with symbols, right? It's very symbolic. Now, where do you go from here? Nowhere. That's the answer. Done. Finito, right? Okay, so that should be the answer, but let's go at an alternative, right? For this problem, can we find another solution? By the way, if you want to know what this number is, exactly you can't find it because these are transcendental numbers. But with a calculator, you can find approximate values. So you can write it as a plus bi, which is important because it's the name of this channel. Don't forget that, okay? And also don't forget that I squared is equal to -1. But if you do forget, go ahead and check out. You know what to check out, right? Cool. Now, let's go ahead and take a look at an alternative method, which I could probably call second method. So what do we have? ln iz equals e to the power I times pi over 2. Oops, no, there's no e, right? It's just I. Okay, never mind. I just overeat it. So that should be I times pi over 2 minus 1. Beautiful. Now here's what I'm going to do. I have an ln. I have the ln of a product. So can't I just write it as the sum of two ln's? I should be able to, right? ln I plus ln z equals I times pi over 2 minus 1. And also, let me distribute this. Because why not? And if you distribute, you get I pi over 2 minus I. Easy, right? Now let's go ahead and evaluate ln I. But what is ln I? ln of a complex number z can be written as ln absolute value of z plus I times the argument of z. But of course, in this case, I'm using any argument. You can always add multiples of 2 pi. So if you want to take the principal value, because this is multi-valued, okay, then you must use a capital arg, and that would indicate the principal argument, which is the one that is between, I think, -pi and pi, or something like that. Anyways, so now let's go ahead and simplify this according to this rule. ln I is going to be ln 1 plus I times pi over 2. ln 1 is 0, so it's going to be I times pi over 2 plus ln z equals I times pi over 2 minus I. Awesome. Now we can go ahead and cancel out I pi over 2 because we can subtract it from both sides and we get ln z equals -I. And from here, this is base e. So z becomes e to the power -I, which is cosine 1 minus I sine 1 as before. And this almost brings us to the end, but we're going to check the value from Wolfram alpha. All right, that's the answer. Let's go ahead and check out Wolfram alpha. Hopefully I did not forget. And yes, I didn't. This is the answer. Do you like that? I think my answer is better. But anyways, we'll give Wolfram alpha some credit. And this brings us to the end of this video. Thanks for watching. I hope you enjoyed it. Please let me know. Don't forget to comment, like, and subscribe. I'll see you next time with another video. Until then, be safe, take care, and bye-bye.